Hi, I'm Sean. Welcome to my course, Data Structures and Algorithms. In this first introduction lecture, I'm gonna talk about why should we know data structures and algorithms. What are data structures and algorithms? The analysis of program complexities, as well as what the topics will be covered in this course. So let's get started. As you may heard a famous word, algorithms plus data structures equal to programs. This is actually a book name written by Nicholas Wirth in 1976. Data structures and algorithms is one of the cornerstones of computer science. Even though technology has changed fast recently, data structures and algorithms remain stable. That means it's worth for us to take effort onto it. Besides, data structures and algorithms can help us become better problem solvers and write efficient programs. They can not only help us become more excellent at our work, but also can help us be successful in technical interviews. And more importantly, data structures and algorithms can make our life better. They provide us the framework for thinking and solving problems in our daily lives, as well as helping with improvement of our brain's thinking ability. Now, let's talk about data structures. Different types of data can be organized in different structures for efficient access. Just like we put our books on the bookshelf and our clothes in the closet, data structures solve the problem on how to store data for efficient access. And an algorithm is actually a sequence of instructions for solving a problem, such as the following steps to make a cup of drip coffee. What we need to do is firstly weight and grind coffee beans, and then we need to fill water reservoir, and after that we add ground coffee to filter. And finally, we brew it and to make a cup of drip coffee. The algorithm can break down the problem into a step-by-step instructions and answer the question that how should we write the code to solve the problem efficiently. Here is a list of the common data structures and algorithms that will be covered in this course. The data structures can usually be divided into linear data structures such as arrays, linked lists, stacks, and queues, etc., as well as nonlinear data structures such as hash tables, trees, graphs, etc. We will cover two kinds of important algorithms in this course. They are sorting algorithms such as selection sort, insertion sort, merge sort, quick sort, etc., as well as searching algorithms such as binary search, breadth first search, depth first search, etc. And what we also will be cover four important algorithmic thinking approaches in this course. They are greedy, divide and conquer, backtracking, as well as dynamic programming. Now, let's talk about analysis of program complexities. As the input size grows, the time and space to run the program grow correspondingly. An efficient program usually requires lower time and space growth rates, which can be described by asymptotic time and space complexity. However, when the input data size is the same, the data arrangement can be quite different, so the program's time and space complexity can vary. For example, in order to find the maximum number within an array, in the first scenario, what if the numbers in this array are already sorted ascendingly? What we need to do is to access the tail of this array. But in the second scenario, what if the numbers are randomized in this array? In order to find the maximum number within this array, we need to traverse this array and access each element within this array, make comparison, and finally to find the maximum number. There are three important notations based on the different scenario to describe the complexity of algorithms. The first one is the best case scenario. We use big omega notation to describe the program's time and space complexity. In the average case scenario, we use big theta notation to describe the program time and space complexity. And in the worst case scenario, we use big O notation to describe the program's time and space complexity. The big O notation is mostly commonly used notation, since we always need to find some guarantees of the time as well as the space consumed by this program in order to avoid that program running out of time as well as memory. There are three important principles for estimating the program complexities. The multiplication principle. It states that the complexity of nested steps should be multiplied together. And the second one is addition principle. It states that the complexity of the same level steps should be added together. And the third one is the maximum growth rate principle. It states that in order to estimate the total complexity of this program, we only need to consider the maximum growth rate. As we can see in the following example, we have a program that have the input data size of n, and in this case, we use the time complexity for demonstration. This program takes 3 steps to execute. The first step takes 2 unit times to execute, and the second step has the nested loop. The outer loop takes n unit time to execute, and the inner loop takes 3n plus 1 unit time to execute. And step 3 takes 1 unit time to execute. As we can see, if we take a closer look at the step 2, based on the multiplication principle, the total time complexity of step 2 should be the n multiplies 3n plus 1 unit time complexity. And we can also notice that step 1, step 2, and step 3 are all in the same level. So based on addition principle, we should add this complexity of these 3 steps together. So the total time complexity of this program will be 2 plus n times 3n plus 1 time complexity. But it can be simplified using the maximum growth rate principle. We only need to consider the maximum growth rate in this formula. And we can notice that the maximum growth rate is n squared. So the total time complexity of this program will be O(n) squared. If we take a look at the right hand side graph, there are various different complexity of the program. In some cases, the problem are pretty easy to solve. We can write the program to solve it using the constant or logarithmic time and space complexity. For medium level complexity program, it may take linear as well as log linear time or space complexity. For the harder problem, it may require us to write the program takes a quadratic or even exponential time or space complexity to execute. And for the problems with the time complexity of non-polynomial magnitude, we call it NP. It stands for non-deterministic polynomial. Next, we're going to talk about what is this course all about. This course will cover some data structures and algorithm concepts, which includes commonly used data structures and algorithms, and also talk about the problem-solving techniques, including patterns or frameworks used for solving various data structures and algorithm problems, as well as provide you some practical examples from real-world projects as well as lead code questions. As for the prerequisites of this course, we expect that you be comfortable with at least one programming language. And this course mainly uses Java to solve most of the problems. And the secrets to become successful in this course will be understanding the concepts, patterns, or frameworks of the data structures and algorithm problems, as well as keep practicing. Now, to summary, data structures and algorithms lays the foundation of computer science. Algorithms plus data structures equal to programs. Data structures answer the question of how to store data for efficient access, and algorithms answer the question of how to use data to solve problems efficiently. And we have talked about three important notations in estimating program time and space complexities. In the best case scenario, we use big omega notation to describe the time and space complexity. In the average case scenario, we use big theta notation to describe the time and space complexity. And in the worst case scenario, we use big O notation to describe the time and space complexity. And the big O notation is the mostly commonly used notation in estimating the program's time and space complexities. And this course covers concepts of data structures and algorithms, common patterns or frameworks for solving data structures and algorithm problems, as well as practical examples from real-world projects as well as lead code questions. Finally, data structures and algorithms can not only help our work better, but they can also help our lives better. Thanks for your attention. I'm looking forward to seeing you in the next lecture.